Welcome back. Thanks everybody for coming. So this is lecture number 5, and I just wanted to show this again. This is the timeline of the course. So if you're here, you've made it through the first 4 lectures, so congratulations. And now we're in the second half of the lecture series. And the second half is going to be a little bit different than the first because it's more speculative. We've kind of covered the things that we know about neutrinos, and this half is going to be more about what we don't know. So this is going to be really cutting-edge stuff. And I'm really excited about this lecture today because it's kind of at the heart of why we study neutrino physics, neutrino mass and double beta decay as two really important concepts in modern-day neutrino research. Okay, so I wanted to start this lecture with just a review of the standard model. This is a diagram that I've shown before. It outlines all the fundamental particles that we know about. So on the top, you have the quarks, shown with green here. And then on the bottom, you have the leptons. So the electron, the muon, and the tau, they all kind of behave the same way. They're just heavier versions of each other. And each one of those leptons is associated with a neutrino. So an electron neutrino, a muon neutrino, or a tau neutrino. All of these particles, their interactions can be described by the forces. So these are shown in blue on the right side. You have the photon represented with a gamma for the electromagnetic interaction. The gluon with a G, that's the strong interaction that binds nuclei together. And then you have the weak bosons, so for the weak nuclear force, the Z and the W. And we'll talk about some of these today. And then also the Higgs that was discovered in 2012 at the LHC. That will also make an appearance today. Okay, so these are the particles that we know about. And just a review of how these pieces fit together. So I've drawn here 2 diagrams of how we represent particle interactions. So on the left diagram, we have what we call an electromagnetic interaction. And this diagram can be represented with a positron, which is an anti-electron, so a positive charged electron, annihilating with an electron of negative charge. And we talk about the forces that are involved in this process as the exchange of these force carrier particles. So the photon, in this case, carries the electromagnetic force, and it mediates this annihilation process. And at the end of that, what you get is an energy release in the form of another electron and a positron. So the particles haven't changed, but the 2 particles have come together, interacted somehow, and then 2 particles leave the interaction. Another example of this is the weak interaction, shown here on the right. So in this case, we have particles that actually do change. So the weak interaction changes particle type. We have a neutrino, an electron neutrino coming in. It exchanges this W boson, so it experiences the weak interaction or the weak force, and it converts that electron neutrino into an electron. And then in the process, it also changes the quark that it interacted with. So this electron neutrino has interacted with an up quark. After the weak interaction, it changes into a down quark. And this process or these diagrams show how these particles interact and what the standard model is all about. Oh, yeah.
On that, the left diagram, so you have the force mediating there being the photon, and I've heard the term exchange of virtual particles and exchanges, which to me suggests that there's 2, one going each way, and is there a single direction to that, or is there?
Okay, good question. So these diagrams, actually, you can rotate them any direction. The only thing you have to be careful about when you rotate the diagrams is that make sure you get the charges correct.
But there's only one photon involved in this.
That's correct. Yeah.
So it has to go from A to B.
It
doesn't matter which way.
That's right. Yeah. Okay, so the standard model, we have all these particles, but one thing the standard model doesn't tell us is the masses of the particles. So in particular, the quarks and the leptons, those masses we have to go out and measure. We have to design an experiment to go produce a muon and then find some way to measure that muon, for example. So the standard model masses look like this, and these are plotted on a log scale here. So you can see that all of the particles of the standard model are kind of clustered on this side, but the neutrinos, they don't make an appearance over here. We know that the neutrinos are at least 1 million times lighter than everything else. So the photon, that has 0 mass, but the neutrinos, we know they have mass, but for some strange reason, they're about 1 million times lighter than everything else we know. So I just wanted to bring up the evidence that we have for neutrino mass. And we've talked about this in previous lectures, and it comes from oscillations. So in particular, the electron neutrino doesn't stay an electron neutrino as it travels. It switches between electron neutrino, muon neutrino, and tau neutrino. And we can see that from different neutrino sources. So if we look at our data that we've collected over the decades, we have evidence of this from neutrinos that were produced in the sky. So neutrinos that are produced in the atmosphere, we can detect those on Earth, and we see that the flavor of the neutrino changes as the baseline changes. That's shown in this plot here from Super Kamiokande. We can do the same thing with reactor neutrinos. We can produce neutrinos at nuclear reactors, and as those neutrinos reach our detector, there's some energy-dependent or baseline-dependent effect that causes the flavors to change. Same thing with the sun. Solar neutrinos also exhibit this behavior. And then neutrino beams, where we have a very precisely controlled beam of muon neutrinos. We can see that that beam of muon neutrinos does not stay muon neutrinos by the time it reaches our detector. And this process can only happen if the neutrinos have mass. So what we really need are mass measurements. And I mentioned that oscillations that show us that the neutrino have mass, but they have one Achilles heel, which is that they only tell us the mass differences. And the reason for that is due to the frequency of the oscillation. The frequency is set by the difference between mass 1 and mass 2, for example, in the neutrinos. So we can't use oscillations to measure the masses directly. All we know is the differences between the different masses. And then we have this question about why neutrinos are so much lighter than all the other particles in the standard model. And then finally, really at the core of all of this is that the standard model doesn't tell us how the neutrino gets mass. So there are different ways that particles can have mass, and we'll talk about some of those in this lecture. Okay, so lecture 5, neutrino mass and double beta decay. So we're going to start with part 1, which is weighing the neutrino. How would we design an experiment to measure the mass of the neutrino? So first I want to just mention that this is kind of a loaded question. So mass of a neutrino is not really a well-defined thing. So as we talked about with oscillations in previous lectures, we have 3 neutrino flavors, so the electron neutrino, the muon neutrino, and the tau neutrino. But those are superpositions of what we call the mass states. So what is actually traveling, what has a definite mass. So if we measured an electron neutrino, we wouldn't just get one of these things. Instead, we say that these things are in a superposition. So the electron neutrino can be thought of as a combination of nu1 plus nu2 plus nu3, and each of those things have a probability of being observed when you detect the electron neutrino. So this diagram here is just showing that the different neutrino flavors have different mappings to the different mass states. The electron neutrino has a large probability of being detected as nu1 and a smaller probability of detecting as nu3, and this changes for all the different neutrino flavors. And we learn this mapping through oscillations, but again, we don't measure what the actual masses are, just the differences between them. So I've put together a cutting-edge experiment that I'm calling a neutrino mass spectrometer. So I'm taking an electron neutrino and I'm putting it on a scale. So this doesn't exist, but if it did, what you would see if you measured enough electron neutrinos is this kind of distribution forming. So the vertical axis in this plot here is showing the number of electron neutrinos you've observed, and then the horizontal axis is the mass. So if I made enough measurements of the mass, what I would see is that for each electron neutrino I got, I would have some probability of getting mass 1, some probability of getting mass 2, and some probability of getting mass 3. And it would be proportional to how much the electron neutrino mixes with those mass states. So this is kind of what we want to do, but in reality we have a lot more challenges than this. So what I showed on the previous page was kind of an ideal detector where you have infinite resolution and you can really probe masses at arbitrarily small distances. But in reality, what we have are detectors that have finite resolutions, and so what we actually see is something more like the right-hand picture, where instead of these nice peaks at each mass point, you just can limit the range of the masses to a kind of narrow band. So representing that with just a block, you would every time you measure the neutrino, you could say its mass is between 0.5 and 1 eV. And this would be a really, really good detector if we could do it at this scale. So for all intents and purposes, the masses of the neutrinos that we measure are going to be some kind of weighted combination of the mass states that the neutrino is in a superposition of. Okay, The other thing is that when we measure neutrinos, we have an indirect measurement. So having a neutrino at rest on a scale is also very impractical because the neutrino doesn't have electromagnetic interactions. We can't confine it in any way. We can't slow it down. It just travels. So what we're talking about when we're measuring neutrino mass is looking at the products that the neutrino produces in its interaction, so the particles that go out of its interactions, and trying to infer the neutrino mass from them. So I have two examples shown here on the right. The first one is where a neutrino interacts with a nucleus and it produces a proton, an electron, and then a recoiling nucleus. The second case is where you have a nucleus at rest and then that decays and it produces a neutrino and also a charged particle in association with it. So the things we're measuring are, the things we're measuring are these particles in the final state is what we call it. So the initial state would be the neutrino and the nucleus in this top example, and then the final state would be the proton, the electron, and the recoiling nucleus. In the example down here, the initial state is the nucleon at rest, and the final state is the nucleon and the electron that we can actually measure. So we don't see the neutrino. Now, there are a couple ways to measure neutrino mass, and one of them is actually to use natural sources of neutrinos. So I talked about last time about supernova neutrinos, where as the supernova explodes, neutrinos are emitted, and this happens over distances of thousands of light years. And this is actually a really unique laboratory where you can test properties of neutrinos. So in particular, as the supernova goes off, you have these neutrinos emitted. And based on the velocity of those neutrinos and the distance to the supernova, you can infer something about if the neutrino was traveling at the speed of light or slightly less than the speed of light. So the way this would work is you figure out what time the supernova went off, and you checked in your detector on Earth what time the neutrinos interacted. And from that, you could extract what the mass of the neutrino could be based on if the neutrino arrived a little bit too late. So here I just have an example of a detector. These neutrinos from the supernova travel over 100,000 light years. They reach us on Earth. They interact in your detector, and you look at this electron that is produced when the neutrino interacts. And based on the model of the supernova, you can say, okay, well, I saw all these electrons appear in my detector at this time. The neutrinos, those were caused by neutrinos from the supernova. What could the mass be? And so people have done this using the one supernova that we've detected. So this is a picture from James Webb of supernova 1987A, imaged in different colors to make a kind of composite image. And this is all of the world's neutrino data that we have from this one supernova. So this is showing on the vertical axis the energies, and then the horizontal axis are the times. And so based on this, and from models of how supernovas evolve, you can make a statement with a limit on how heavy the neutrino could possibly be. Otherwise, you would start to see effects of the neutrinos lagging behind when they arrived. And the number you get about from doing this with supernova is about 10 electron volts. So this is one way to do it, but unfortunately you have to wait for a supernova, which could take a long time. And second of all, it has a lot of uncertainties. So uncertainties on how the supernova has evolved and how the neutrinos are emitted from the supernova. So the question we should be asking is, can we do better? And what would a dedicated experiment look like that could really measure neutrino mass? So going back to one of the oldest tricks in the book, which is beta decay. This is the method that we use to discover the neutrino in the first place, where you start with an atom and you wait some time, and then after a while, it decays into a different atom plus an electron, which we call a beta particle, and an anti-electron neutrino. So this process, you can ask what the energy is of this process to say something about the mass of the neutrino. And the way this works is by looking at conservation of energy. So back in the first lecture when I introduced beta decay, we differentiated it from another decay called alpha decay. And in alpha decay, the alpha particle gets all of the energy. And so it was very clear that energy was conserved in this process. But when the neutrino was being discovered, it was not clear what was going on. It wasn't clear that there was a second particle in the beta decay. So now we understand that in a beta decay, the energy is kind of split between the neutrino and the outgoing electron. And so energy is still conserved, but again, like in all of our other examples, you never observe the neutrino directly. You only observe this electron. So conservation of energy still holds, but the way we can measure mass is by looking at the energy of the neutrino of the electron, and knowing the total energy very well, and trying to infer what this neutrino energy was based on those two numbers. So here's another kind of cartoon version of the beta decay spectrum. On the vertical axis is showing the number of electrons, and then the horizontal axis is showing what those electrons' energy is. And so by the principle of energy conservation, what we can do is we can say that the energy of the electron has to equal the energy we started with, which we'll call E0, and then the energy of the neutrino, E nu. And what you can do is you can zoom in to the endpoint of this spectrum, so the very highest energies of the electron. And by energy conservation, if the electron has the most energy, then the neutrino should have the least energy. But if the neutrino has mass, then the least energy the neutrino can have is given by the mass of the neutrino. So if we zoom in even further, we can start to look at what the endpoint of this spectrum would look like. So I have two cases shown here. If we zoom in, the case where the neutrino has 0 mass would look like this blue line. So in other words, the electron could infinitely approach the maximum energy it could have, and we would have to do many experiments to try to observe an electron with that energy, but it would be kind of a continuous spectrum. On the other hand, if the neutrino has mass, then the electron should have a maximum amount of energy that's somewhere below what it would have if the neutrino had 0 mass. So in other words, the spectrum would be distorted a little bit at the end based on the difference of the neutrino mass with 0. So how heavy the neutrino is would be some kind of distortion of the spectrum just in this region here. So that's the idea, and the experiment we're going to do requires producing or has some pretty strict requirements. So first of all, in order to do this experiment where you actually look at the endpoint of this beta decay spectrum, you need a source that has a lot of beta decays. And the reason for that is because most of the beta decays, I'll just go back for a second, most of the beta decays are happening here. So most electrons that you get out of a beta decay are going to have the energy split in close to 50-50, let's say. But the ones you're interested in are all the way at the end. So you need something that produces a lot of beta decays to give you a good chance of seeing one that's near the endpoint here. The other thing you need is low endpoint energy. So I talked about the neutrino mass being less than or 1 million times lighter than the electron, for example. So that means that when you measure the electron energy, what you need to do is have a detector that is sensitive to those levels of mass. So in other words, if your energy is very high, then your detector is going to have different backgrounds that could interfere with the measurement. And then finally, it helps to have a very simple source here. So the simplicity of the source helps you predict the spectrum theoretically using equations so that you can really say whether or not you've seen a distortion or not. And it turns out there is one element that is suitable for this, and it's tritium. So tritium is a nucleus composed of 1 proton and 2 neutrons, and its half-life is about 12 years. So if you get a lot of them in one place, then you get a lot of decays. The energy of the endpoint is also pretty low, so 19 keV. This is about factor, let's see. It's pretty low compared to a lot of experiments that are out there. So the experiment that we're going to do is take a tritium source, and that's going to be undergoing a lot of beta decays. It's producing a lot of electrons, and then we're going to try to filter out the ones that we want. So filter out the ones that are close to the endpoint of the spectrum. So, and then count the electrons that make it past that filter. So the idea here is that most of the electrons we just don't care about. They're not close to the endpoint. But the ones that are close to the endpoint have enough energy, and we want to count how many actually make it past. And then we'll tune where that threshold is to try to count the electrons that make it and find out that point at which the electrons make it to the detector. That will tell us where the endpoint actually is. Okay, so the experiment that is designed to do this is called Katrin. It's in Germany. It's the Karlsruhe tritium neutrino experiment. And it looks like this. It's a big line of mostly magnets and cleaning for filtering. But it all starts here at the tritium source. So tritium atoms decay here, and then they are transported along this line into this huge thing called the main spectrometer. So I want to talk about the main spectrometer a little bit because this is kind of where the filtering happens for this experiment. So it looks like this. It's called the MAC-E spectrometer, which stands for Magnetic Adiabatic Collimator with Electrostatic Filter. And it's quite an impressive thing. And the reason it looks like this, I'll talk about shortly. But first, I want to talk a little bit about how this detector was assembled. So it was built here in Deggendorf, Germany, and then the lab site was in Karlsruhe, as I mentioned before. It looks like they're pretty close together, but actually this spectrometer was so big that it couldn't use the roads, so its actual path looked like this. The detector had to travel on rivers across Europe, so it first made its way down here through around Greece, and then it eventually made it out into the Black Sea, and then came around Turkey, Italy, up through France, and then back up to the northern part of Germany. So it was quite an exciting move. It had to be loaded onto ships and then unloaded, and then finally it made its last leg on the roads through some small German towns, which was really great. So very exciting experiment. But the whole point of this is summarized in this diagram. So it's kind of complicated, but we'll try to break it down. So the electrons from the beta decay enter the spectrometer on one side, and then there are several options that can happen. So the first thing is that this whole spectrometer is under a magnetic field, and the magnetic field varies throughout the spectrometer. So on one end, or actually on both ends, there's a very high magnetic field, and on the middle there's a low magnetic field. And what that does is it very slowly alters the force that's felt by each electron as they pass through, such that in the middle, where there's no electric field, all the electrons get lined up in one way. And that allows you to do the filtering, which we'll talk about next. So this little inset down here is showing that the electron could come into the detector with any orientation, but by the time it gets to the middle, it's been slowly rotated into a plane that's lined up with the spectrometer. And then, at the end, it gets rotated back, but the orientation doesn't matter at the end. The whole point is that it's focused in one direction at the middle. Because at the middle, what we have is a filter. And the filter is created using electrodes. And those electrodes create an electric potential that only allow electrons with certain energies to get through. So the diagram here is showing in this first track A, this is an electron that has enough energy to make it past the filter. So what it looks like on this slice, if you were to slice this through and plot the energy of the potential barrier that's created by these electrodes, you would have this track A is this electron that's passing over the potential barrier. On the other hand, if the electron doesn't have enough energy, then it's rejected. So it doesn't have enough energy to pass this barrier, so it gets bounced back. And you wouldn't count that electron. The other thing that can happen is that you can have some backgrounds in this experiment. So this red track is showing what would happen if a charge didn't enter through the spectrometer, but instead kind of appeared in the middle because a cosmic ray interacted or there was some radiation. That would all get trapped in the spectrometer. So the spectrometer also is blocking radiation. So at the end, at the end, the electrons are counted, and this is what that count data looks like. So this vertical axis is showing how many electrons have passed the filter, and then the horizontal axis here is what the filter value is set at. So as you increase the filter value, fewer and fewer electrons pass your filter, and you're trying to map out what happens in this critical region here. So what filter value gives you the endpoint of the spectrum. So that's the way this plot works. This is actual Catron data. And then another thing that they do is they segment their detector into different regions. And that allows them to estimate the background in each region separately. So that's why you have multiple lines here that are all kind of offset from each other. But anyway, it's really this critical region that they care about to measure the neutrino mass. And so when the rate goes to zero. And the experiment was just, new results came out in 2024 from this experiment, and what they determined was that the mass of the neutrino is less than 0.5 eV. So we do much better than the supernova with this kind of experiment. And you can see here that the results have steadily been getting better as they've collected more and more data. This is pretty exciting that 2024 we had new results on this. Okay, I'm going to talk a little bit about a somewhat related concept, which is neutrino size. And this is very relevant because an experiment just came out this year, actually with a new result on the neutrino size. So it's closely related to the mass in that some of the concepts that were used in this experiment are important for mass measurements. So the way this experiment worked, it's called BEAST, and I forget what it stands for, but the BE is beryllium, because what they start with is a beryllium atom, and there's an electron orbiting around the beryllium atom. And sometimes what happens is that electron can be captured and create and put the nucleus in an unstable state, which then decays. And in that decay, you have the recoiling nucleus and a neutrino produced. So that recoiling nucleus is what this experiment is trying to measure. And the way they do that is a very clever detector where they have a crystal lattice and they embed these beryllium nuclei in it. And then that whole thing is in a superconductor. And when there's a decay, that superconductor, you can read out the current from it very precisely. So you get very good energy resolution on this. So what the BEAST experiment did is that they used the Heisenberg uncertainty principle, which is a concept that relates the uncertainty in a particle's position with the uncertainty in a particle's momentum. So by measuring the momentum of this recoiling nucleus very precisely, they're able to infer what the uncertainty is on its direction. And so in other words, if you have a very precise knowledge of the particle's momentum after the recoil, then that sets the scale of how uncertain the localization of that particle is. So in other words, where that decay happened in space. So the relationship here is that the better you know the momentum, so the smaller sigma p is, the larger sigma x is. So the better you know the momentum, the worse you know the position, or the larger range the position can have. So what they did is they measured this, and because the recoiling nucleus is related to the neutrino through quantum superposition, they were able to extract that the position of the neutrino has to be localized to a pretty large area. So in this diagram here, I'm showing just the position, which we're calling x. And this red band here shows the overlap of where the neutrino could have been after the decay relative to the nucleus. So the kind of critical thing here is that they found that could extend beyond the nucleus, actually. So the localization of the neutrino in this measurement is not known it has to be larger than the nucleus itself. So this is kind of an interesting technique that you can do. And we'll revisit electron capture a little bit later. Okay, so part 2 of this talk is all about the neutrino mass mechanism. So we've talked about neutrino mass and we've talked about how you can measure that, but let's talk about fundamentally what is neutrino mass. So back to the standard model, I want to highlight this block of the standard model with the quarks and the leptons. So these are what we know as fermions, and the reason that we call them fermions is because they all share a property called spin. And spin for these fermions is 1/2. And we'll talk about what spin is just now. So spin is a concept where a particle can either be left-handed or right-handed, depending on the direction of its spin. And spin is really, you can think about it as intrinsic angular momentum. So you can imagine something spinning around an axis, for example. And the reason we call it left-handed or right-handed is because we have the right-handed rule that you might have heard from electromagnetism. You take your right hand with your thumb sticking up, showing the direction of motion, and then your fingers wrap around the direction that it's spinning. So right-handed would be like a particle moving this way with its spin kind of coming towards me. Left-handed would be a particle going this way with its spin coming towards me. And you can flip these around just using your hands to figure out which handedness the particle has. So in the standard model, we have all these particles, but the particles can have different spins. So there's nothing inherently special about spin. You can have an electron that's spinning one way or an electron that's spinning another way. So here I'm just denoting which direction the particle is spinning by putting a little subscript here. So electron with a subscript L is a left-handed electron. Electron with a subscript R is a right-handed electron. And then these arrows indicate the direction of the particle with the direction it's spinning. So for the left-handed one, it's going this way. The spin is coming kind of up and around. And the other one, the spin is going the other way. I need to use my right hand for this one for the same direction. So that's what we mean when we talk about handedness. And this becomes relevant because our model of fermion mass, of how the fermions get their masses, has to do with this handedness. So what we know is that we have the standard model predicts that the interaction rate of the fermions with the Higgs boson should tell you something about the mass. The mass should be related to how the fermions interact with the Higgs. And the Higgs, we know it's a particle itself, but it also provides a field that exists everywhere in space. So the kind of model that we have generated over the years is that fermions, as they travel through space, they interact with the Higgs field, and each time they do that, they switch handedness from left to right and then back again. And the more times you interact, so in other words, how strongly you interact with the Higgs field, is kind of like a drag. It kind of influences the mass of the particle. So if you interact more, you should be a heavier particle. If you interact less, you should be a lighter particle.
What is the interaction mechanism? There's no interaction mechanism here, just contact.
Okay, yeah, so the question was what the interaction mechanism is. Yeah, so at the beginning I showed those diagrams where you have particles interacting and then you have a boson in between. You can put the Higgs there, for example, in one of those diagrams. Yeah.
So interaction with the Higgs field
is
not interaction with the Higgs excitation.
right. Interaction. Yeah, exactly.
It's a contact.
Yeah, so this model is actually really successful. And I'm going to go to talk about a little bit from colliders. So from the world of particle colliders, especially the LHC, we've actually done the experiment where the LHC has produced these Higgs bosons and watched them decay into different fermions. And what they find is this plot that really beautifully shows that the coupling strength, so how often the Higgs is decaying to each fermion, is proportional to the fermion's mass. So this model really describes reality to very high precision. So you can see that the muon down here with a very low mass, the Higgs doesn't decay into it very often. And it's just a really nice linear relationship for all the different particles that have been observed at the LHC. The problem is that this muon was a very challenging measurement to happen because the muon is so light. Because this interaction doesn't happen very often, this is kind of the latest data that came out, I think in 2020 or pretty recently. And to go even below that, to do the same experiment with electrons or neutrinos, you're talking about rates that are 1 million times lower, for example. So it's kind of impractical to do this with the lightest particles like the neutrino. But we do know that this mechanism works for heavier particles, or by looking at heavier particles. So I'm going to talk about two kind of fundamental experiments that were done in the 50s that kind of showed us that something might be amiss. So the first one is the looking in the mirror experiment, and this was done by Qinxing Wu, where she was looking at how particles decayed that had different spins. So in particular, if you take a particle that's spinning, and you look at it in the mirror, it changes handedness. So a left-handed particle looks like a right-handed particle in the mirror, and a right-handed particle looks like a left-handed particle in the mirror. So the question is, does this have any impact on a particle interaction or on a nuclear decay? And the experiment worked like this. Take a collection of cobalt-60 atoms. Those are spinning in some direction, and you can align all of the spins to the same direction in a magnetic field. And you can do that with the magnetic field either going up or down, and you can change the handedness. So the particle is still at rest. It's just sitting there spinning in place. You can think of it like that. And if this is really a mirror picture, then what happens is, or that what happens in one picture should be the same as what happens in the other picture. So in other words, every time this cobalt-60 atom decays, the electron and the neutrino that come out of the decay should go in any direction because it needs to look the same whether or not you're in a mirror or not. All you're really doing is changing the direction of spin, but there should be no preferred direction of the decay products in this interaction. So when the cobalt-60 atom decays, it becomes a nickel-60 atom, and it's still spinning in that same direction. So you can do this experiment with a right-handed spinning nucleus and a left-handed spinning nucleus. But what was actually observed, though, was that the decay products came out of this decay in a preferred direction, and that direction was aligned with the spin of the particle. So it's a very strange experiment because what it's basically saying is that if you take a particle interaction and you look at it in a mirror, it's flipped. It's not a perfect mirror. It's not really reflecting what the interaction was doing. There's something fundamentally different about it. So we call this, the technical term for this is parity violation, which means that parity is just a position swap. So you've swapped from one perspective to another perspective, And it shouldn't look any different, but it does. So in the case of the right-handed spin, the electron is emitted going down, and in the case of the left-handed spin, the electron is emitted up. And this experiment only ever observed the decays happen in this way. It wasn't even close. There was no ambiguity about it. Every time you had a collection of upward or right-handed spins, the electron would be emitted down. Every time you had a collection of left-going spins, the electron would be emitted up. So it totally violated parity. So the reflection is different. The interpretation of this experiment can kind of be summarized like this. If your initial direction of spin is represented by this arrow, then the decay of the spinning nucleus looks like this. And there's an anti-electron neutrino, and what you have to do is kind of make this arrow work out. So the particles that come out of the decay after the initial have to add up to the same spin as the initial system. So we have three particles in the final state. We have this anti-electron neutrino. We have this nucleus. This is the nickel nucleus that was the product of the cobalt decay. And then you have this electron. And if you look at the directions relative to how they're spinning, you can draw these arrows that show the direction of their spin relative to their motion. So you need a right-handed antineutrino. You need a right-handed nickel nucleus, which could be measured experimentally, and then you need a left-handed electron. And so in other words, what was never observed is if you swapped the anti-electron neutrino and the electron. So if I now put the electron on the other side and then the anti-electron neutrino on the bottom, going in the opposite direction, this was never observed. Even though you could line up the arrows like this, this process never happened. So this is one clue. The second clue came from the Goldhaber experiment in 1958. So this, instead of starting with a nucleus that had spin, start with a nucleus that had zero spin, and then try to infer what the spin of the neutrino was after this reaction. So the nucleus that was chosen was europium-152, I think, so kind of a esoteric nucleus, but this decayed into samarium-152, and in particular, it decayed into a particular state of samarium that was excited. And this is important because when the samarium is in an excited state, it emits not just the neutrino, but it also emits a photon, and you can measure the photon very precisely. So what was done was to start with this europium atom, spin 0, so not spinning at all, and then at the other end of the decay, you have to conserve the spin that you started with. So you know that, so this samarium atom recoils and then it emits a photon because it's excited, and you know that the spin of this photon has to be the same as the spin of the neutrino because you started with spin 0. And what was observed is that every single time this happened, the neutrino or the photon was always left-handed, and you can infer that then the neutrino had to always be left-handed in this interaction too. So to summarize what we've learned from these two experiments, you can do it with this picture of what we call the weak interaction handshake. So on the top, I have just on the right side of this, the W boson of the weak interaction, so the weak force, and then particles with particular spins. So for example, an electron and then a neutrino, and both of these have to have left spins to shake hands with the W boson to actually feel the force. What's never observed is this, where you have a right spinning electron and a right spinning neutrino. Those don't interact with the weak force. So the summary of this is that the weak interaction only happens for left-handed particles and right-handed antiparticles. And this is kind of crucial because what we're basically saying is that we have two neutrinos, but four neutrino states. But if the two states on the right here, so the anti-neutrino with a left spin and the neutrino with a right spin, those would never be observed. So this picture where we have particles interacting with the Higgs boson field to give them mass, that doesn't really work for the neutrinos because we would have to see the right-handed or the left-handed, or the right-handed neutrino or the left-handed antineutrino for that to happen. So the idea here is that maybe this is the case, but it's very hard to verify because because the neutrino only has weak interactions, but if there are other states of the neutrino that don't even have weak interactions, then how would we ever see them? But there was one idea, so unless that these things are actually the same. And the reason this works is because you can look at these particles, so the left-handed neutrino and the left-handed antineutrino, and ask what their quantum numbers are, what numbers describe them. So both of the particles have the same handedness, so they're both left-handed. They're both chargeless, they both have 0 charge. And they both have the same mass because they're both just neutrinos. So maybe these particles are actually the same thing. And you can do the same thing with the antineutrinos that have the right spin that we observe. Maybe they're just the same as the right-handed neutrino. So maybe, really, we're only saying that there are 2 states, and it's just the same particle viewed from different directions, or spinning with a different sign. So this is the idea. Maybe there's only one particle that can be left-handed or right-handed. And really what our experiments are saying is not that there's some other neutrino out there that we can't see, but maybe it's just the same neutrino moving back and forth. But the implication of this is that the neutrino is its own antiparticle. The implication is that as you move from a left-handed neutrino to a right-handed neutrino, it's the same particle, but it's becoming an antiparticle version of itself. And so this would be pretty profound because we don't have any other particles like this in nature. So the 2 cases that we're talking about here are called Dirac or Majorana. And it's one of the great unsolved problems of the Standard Model. So in the Dirac case, which is, again, we have good evidence that there are Dirac particles. Every other particle we know about in the Standard Model behaves this way. The neutrino and the antineutrino would be distinct particles. There would be something different about them besides their mass, their charge, and their spin. But in the Majorana case, which is named after a physicist, Ettore Majorana, then the neutrino and the antineutrino are actually the same particle, and the only thing that differs between them is the handedness of the neutrino. And this would be the first of its kind, so the first particle that we know about that exhibits this behavior. Now, there is actually one way to test if this is the case. And the story starts actually here at the University of Chicago with a very famous physicist, Maria Geppert-Mayer, who you might know because we're in her lecture hall right now. So back in the 30s, when she was working on nuclear theory, she discovered that there was a process where some nuclei could undergo not 1 but 2 beta decays at the same time. And this is a very rare process, but it was implemented to describe why some nuclei were more stable than others. And so the process looks like this. You have some huge nucleus here, and then it emits simultaneously 2 electrons and 2 anti-electron neutrinos. So why is this? Oh, yes, right. And of course, Maria Geppert-Mayer was awarded the Nobel Prize in 1963 for discoveries concerning the nuclear shell structure. So that came after the proposal for double beta decay. So a little bit about why this happens. It's useful to look at a chart like this, where the vertical axis here is something called the mass excess. So the mass excess just means that when you have protons and neutrons arranged into nuclei, they can be more or less energetic than kind of what you would expect just by summing up all the masses of the neutrons and the protons that go into the nuclei. And so in particular, this is kind of representing the energy that goes into the binding of the nuclei. And lower on the mass excess means the element is more stable. And so what is being plotted in this figure here are different elements that have different numbers of protons, but all the same number of protons and neutrons. And it's useful to look at a chart like this because beta decay doesn't change the total number of protons and neutrons in the nucleus. It just switches one neutron into a proton or one proton into a neutron. And so the trend of different atomic nuclei is for them to beta decay down to a place of stability, so kind of at the bottom of this parabola. So if you start as this, I think it's zirconium, you first beta decay to gallium and then germanium, and towards the bottom of this parabola. But for some elements, there's actually kind of a gap where, nuclei decay to more stable configurations, but for some elements, there's actually a gap where you can see on this parabola, if I get to germanium here, now I'm kind of stuck because my next element over is arsenic, but the binding energy of arsenic is actually higher than the binding energy of germanium, so I can't do a beta decay. That would violate energy conservation. So instead, I have to skip over arsenic and go all the way down to selenium. Yeah. And that process is the double beta decay process. So I've now skipped over arsenic and emitted 2 beta particles or 2 electrons to convert 2 protons into 2 neutrons, and now I'm at selenium, which is the more stable configuration. So just as a feature of nuclear physics, sometimes you can have these 2 beta decays happen based on a particular arrangement of the nuclei that are involved. Okay, so why is this important for our neutrino story? Well, it turns out you can have a process called neutrinoless double beta decay, where if the neutrino is its own antiparticle, it can actually annihilate in the beta decay before the electrons are emitted. So the 2 diagrams are shown here. So what Maria Geppert-Mayer showed us is that this process can happen where you have 2 beta decays. But if the neutrino is Majorana, if it's its own antiparticle, then you can also have this process happen too, where the electrons are emitted, but no neutrinos are emitted because they've annihilated, because the neutrino is its own antiparticle. They cancel each other out. So if we could observe this process, it would be definitive evidence that we have a Majorana neutrino. And this process is called neutrinoless double beta decay, sometimes abbreviated 0 nu beta beta. So I'll use those kind of interchangeably. So back to our double beta decay spectrum. So what would this look like? Well, it looks a lot like our regular beta decay spectrum, but now what we can do is look at the energy of both electrons that come out of the beta decay, and then subtract off the energy that comes from the 2 neutrinos. So once again, we have the number of decays on the axis here, and then kind of a spread of energies because the electrons and neutrinos can share the energy in different configurations. But if the neutrino has a double beta decay, if the nucleus has a neutrino-less double beta decay interaction, what would happen is something different than what we saw in the beta decay case. So what would happen is that the electrons would get all of the energy at once. They wouldn't have any of the energy go into the neutrinos. So actually what you would see is kind of a spike at the end of this spectrum where you have a monoenergetic, or every single decay would happen at the same energy. So this would be totally different than what would happen in a beta decay. It would look more like an alpha decay because now you no longer have neutrinos that are being emitted in this process. So the idea is going to be to look for this process, to see if we can actually see in the spectrum an excess here at the endpoint due to neutrinoless double beta decay events. So the rate, how often does this process happen? Well, it turns out it's incredibly rare. So first you have to have an isotope that undergoes double beta decay, which is already pretty rare. And then you have to get lucky where the neutrinos would interfere with each other and annihilate, and you would see a neutrinoless double beta decay experiment. So people have made attempts to calculate this analytically, and what it comes down to is that the rate is proportional to actually the mass of the neutrinos. So the neutrino mass shows up here. It's called, just written here as m beta beta squared. And this is similar to that weighted average of neutrino masses that we had before that the Catron experiment was looking at. So you can think about it as kind of like the sum of the neutrino masses or a weighted average of the sum. There are a couple other components here. So this one has to do with nuclear physics. And it turns out that nuclear physics with very large nuclei is very hard to do. So there's a big uncertainty here that comes from calculating this m term. The last term here is just a particle physics term. It's less uncertain, but it does depend on the isotope. So if you have a heavier isotope, the rate can be increased versus a lighter isotope. Okay, so searching for this, we have actually built experiments to do this. And there are 3 kind of isotopes that have been identified or that current experiments are using to make this measurement. So it's germanium-76, tellurium-130, and then xenon-136. There are about 10 other isotopes that maybe are possible for this search, but there aren't experiments to do them. So there really aren't that many choices that you can have. But each one of these has different advantages and disadvantages. So I'm just going to kind of list out some of them. But the takeaway message is that there's no really clear winner of which isotope to use for this experiment. So germanium is nice for a couple of reasons. You can embed a detector inside a germanium crystal, which makes it really very efficient at seeing what happens inside the crystal. But it's expensive because it's very rare to process it, and it's also pretty light. So it's got this mass number 76 here compared to the other ones, which are 130. So the rate of the double beta decay is a little bit less. Tellurium's nice because it's heavy and it's naturally abundant, so it's kind of cheap. But to read out a tellurium crystal, as we'll see in a couple slides, is actually kind of slow, so there's some backgrounds associated with it. And then xenon is also another choice. It has some pros and cons. It's, again, heavier, but you have to liquefy the xenon, and it's hard to put a detector inside liquid xenon, it turns out, so it can make things challenging. But the point here is that there's no clear winner of which one to choose. So we'll just talk about some of the experiments that exist to do this measurement. So the first one I'm going to talk about is Legend, which is using germanium-76. So Legend is based in Italy, and here's a picture of what it looks like. It's strings of germanium detectors that each have a little embedded chip in them to do the readout. So the way this works is that germanium is a semiconductor. And what that means is that whenever there's an electron emitted inside the material, you get a little current between the outside of the detector and a sensor that you can place inside the detector. And so if you have a double beta decay event, you have two electrons kind of appearing out of nowhere. And that creates a charge imbalance that creates a current that you can then read out. So that's the principle of the detection. And then germanium is also nice because if you have a background like a photon, like so from some radiation that comes in and it interacts in your detector, it will produce a couple depositions of energy. And so you can differentiate between these 2 points, these two cases. So you can either have a point-like decay, or you can have a multi-site event that you would consider background. So you can tell the difference between some of the possible cases. The next one is tellurium-130. This is the Quarry experiment. And this is what I was talking about, kind of reading out tellurium can be a little bit slow, but it has some advantages. So each one of these blocks here that you see on the right is a copper enclosure that surrounds a tellurium crystal. And the way this works is that the tellurium crystal is coupled to the copper, and the copper serves as a heat bath. And every time there's an energy deposition inside the tellurium, the temperature changes ever so slightly. And you can read out the temperature change with a temperature sensor, so a thermometer essentially. And as that temperature resets to 0 because it's coupled to the copper, you can see the shape of the temperature change over time and ask questions like if the temperature change is consistent with the neutrinos double beta decay event. So in order to do this experiment, you have to keep this whole thing at very, very cold temperatures because the temperature changes you're looking for are minuscule, so millikelvin scale. And if you remember from the last lecture, we talked about the cosmic microwave background being 2.7 Kelvin. So this is even colder than the cosmic microwave background that they have to keep this detector at. So we refer to it as the coldest cubic meter in the known universe. There's one other story about Quarry, and it actually starts about 2,000 years ago. So imagine you're a Roman soldier floating along the seas, making some deliveries or going to war or something. You're on this boat, and there was a storm, you sank. Okay, so why am I telling you this? Because it turns out that people have been harvesting these Roman shipwrecks in the Mediterranean for a long time. And on the Roman shipwrecks, they find things like metals, so like copper and lead. And in particular, a particular Roman shipwreck had a lot of lead bricks on it. The Romans knew how to make lead, and they made it pretty well. But lead that has been sitting for a while actually has a lot of impurities in it, but those impurities decay over time. So if you're a brick of lead sitting at the bottom of the ocean for 2,000 years, you actually decay into everything, or everything that's not lead decays away, and you're left with a very pure lead brick. And it's actually so pure, it's more pure than what we can make with modern manufacturing methods. So the people in Quarry got this bright idea to actually use the Roman lead from the shipwreck to shield their detector because it blocks radiation and it has no radioactive backgrounds itself. So they teamed up with a museum in Sardinia to get some of this Roman lead, and now they use it as a shield for their detector. Okay, the last experiment I'll mention is CamLand-Zen. This is based on xenon. So back in, I think, lecture 2 we talked about the CamLand experiment and how it was looking at reactor antineutrinos. So it's been repurposed since then, and they put inside the detector a balloon for liquid xenon. And there's about 750 kilograms of liquid xenon in there, and that xenon is monitored continuously by photomultiplier tubes kind of surrounding the outside of the detector. So here's what it looks like if you look down into the top of CamLand. This center piece here is the xenon balloon. And that's the amount of xenon that they're monitoring to see if there's neutrinos double beta decay. So I just want to end with where we stand with neutrinos double beta decay. So this plot is called the lobster plot for obvious reasons, I hope. And it's kind of what we use in the field to monitor our progress towards neutrinoless double beta decay experiments. So it's got a lot to it, but I'll try to walk through. So first of all, the vertical axis here is this m beta beta parameter. So it's kind of like the weighted mass of all the neutrinos. And again, the rate is proportional to this quantity. The other option, or the other axis here, is the mass of the lightest neutrino. So if the neutrino is very light, then you're kind of on this area of the plot, and if it's very heavy, then you're on this area of the plot. And what these bands are showing is where we think neutrinoless double beta decay can happen. The bands are set by neutrino oscillation parameters, so how much the neutrinos mix with the different masses. It actually restricts where neutrinoless double beta decay is possible. And now there are two bands, and those two bands come from the different mass orderings that are possible in neutrinos. So I mentioned before that the oscillations only tell us the mass differences, not the absolute masses themselves. So we actually don't know how the masses are arranged. They could either be in what we call the normal ordering, where the nu3 state of the neutrino is heavier than nu1 and nu2. And that means that the total mass of the neutrinos is lighter than if you switched it around and got the inverted ordering, where nu1 and nu2 are heavier than nu3. So we know that these distances, we know these distances from oscillations, but we don't know the absolute masses. So if there could be two heavy neutrinos or one heavy neutrino, we don't know. But it impacts where we think neutrinoless double beta decay can happen. Next, we have Catron. So we can bring in Catron's measurement to this and ask where Catron is setting a limit on the lightest neutrino mass. So I've drawn Catron as a band kind of over here. The neutrino can't be heavier than 0.5 MeV according to Catron, as we saw it before. So we're coming in from the left with Catron from direct mass measurements. And then our neutrinoless double beta decay experiments are coming in from the top. They're probing the rate of neutrinoless double beta decay, which is proportional to this m beta beta parameter. And the current limits are actually have been updated very recently in the past couple of years. So where we kind of stand right now, there are actually two possibilities. There's kind of an optimistic possibility and a pessimistic possibility. The pessimistic possibility is if we assume that the worst case of that nuclear matrix element that I said was hard to calculate is actually very small. So there's kind of a range of possibilities. But in the optimistic case, we're actually down here. So we're starting to probe the parameter space allowed by neutrinoless double beta decay in the inverted ordering. So we haven't detected neutrinoless double beta decay yet, but experiments are getting sensitive to where we think it's likely to happen. So where these colored blobs are filled in. And the idea over the next decades of neutrino research will be to push these limits down further by making bigger detectors, cleaner detectors, detectors with lower background. So I'm going to end here with just a couple takeaways. So neutrino mass is really at the frontier of particle physics. It's really physics that the standard model has no recipe for. So we really have to figure out in the data what it tells us about neutrino mass. We're also in the process of doing this, building the world's most precise detectors that are either very extreme in low backgrounds or low temperatures. We're building detectors that are incredibly precise to try to narrow in on this problem. And then next week, I'll talk about some implications of neutrino mass, in particular in our evolution of our universe. So thank you. Okay.